Thank you for also thank you for introducing me, and also thank you for inviting me. So far it has been a lovely workshop, and I hope that you also will be liking this presentation. I'm Mark Winands from Maastricht University. This is the building that I'm sitting. This is the standard slide that the university is providing me. So sorry for this boring intro slide. I have a confession to make. I'm not really in machine learning. As most of the talks has been about, I'm more in reasoning, about thinking ahead. And I'm especially doing this in games, trying to figure out a plan of action, taking into account what the opponent could do. And the last 20 years, I've been studying all kinds of adversary search techniques, ranging from classic techniques like alpha-beta search till so-called multicolored tree search, which I'm going to discuss today. Most of my applications has been so far in all kinds of games, ranging from board games to video games. And what I'm going to do today is give you a little bit of background regarding search, multicolored tree search. I will also discuss then at a certain moment that there are also applications for these algorithms. So it's not only about game AI. And in the meantime, I will discuss a little bit of challenges that we have, making them more general, using quantum computing, and in the end, explaining what the hell is going on in the end. So why do these game AI researchers actually exist from the first place? Well, this is one of the first tasks that we actually said that an agent should do, play a board game very well in order to defeat the world champion. And over the decades, we've done a lot of research and using games to test all kinds of algorithms, running from machine learning to all kinds of search techniques. It's basically the Formula One of racing for AI, because we're every time trying to push our engines to the max, trying to engineer them, inventing new data structures and combining them with all kinds of other AI techniques in order to get the best results. And of course, the opponent, other programmers, they come up with their own ID. So there's a great benchmark. There's also a safe benchmark. Instead of OpenAI and releasing your new techniques to the public, we do it first in a board game or a video game. And if something breaks down, okay, it's not too bad. So now, the classic technique that we were always using is so-called heuristic search. We're trying to find a plan of action, taking into account what the opponent could do, and the classic one here is Minimax. Unfortunately, when we start to do that, we start building a kind of tree where we simply look to the actions that we have and the actions of the opponent. But at a certain moment, yeah, this is going to explode and we can't search the whole thing. So what we usually will do, we simply will truncate that tree and we will start making a decision on the values that we give to the leaf nodes, which in the past was usually based on some human-made model, a so-called evaluation function. For instance, chess, you simply counted the number of pieces that you had, the opponent had, and then you weigh them, because a queen is worth more than a pawn. I hope so. Well, in the past years, we also are using neural networks for that, just for the fun of that. And then, based on scoring all the leaf nodes like that, we simply did some backpropagation according to Minimax. Well, this is not a class on game theory. Please forget how this works. But in the end, we simply then were able to find an optimal line of play. And then, as your agent, you simply made a decision, assuming that the opponent would also play optimal. And basically, game playing was actually building these smaller search trees all the time. There's only one small problem. What are you going to do if you don't know anything? So in a lot of games, we could make these nice models that you could assess the board position, like in chess, checkers, shogi. You see some famous people like there. Maybe you still recognize Mr. Kasparov, who nowadays is opposing Putin a lot. He was a chess player once upon a time for the younger generation. But Around the 90s, we were actually pretty good in playing these board games, except for one small exception called Go, where basically human players in those days were actually superior. You could easily give the agent 30 stones ahead and you still won the game. The problem was, what are you going to do if you have no clue to assess a position like this? What are you going to do if you don't have the data to build such an evaluation function automatically through a neural network? What are you going to do if you don't have the resources to build one? Because, well, building a neural network takes a little bit of GPU power. And what are you going to do if after all your efforts, it still fails? You still don't have a nice assessment. What are you going to do? What will your students do on an exam if they don't have a clue? My students always going to gamble. And where can you gamble? In Monte Carlo, of course. There are casinos. So the idea that people had was so-called Monte Carlo evaluation, that at a leaf node, you simply started to play a random simulation until the end and try to score it. And then the idea was, if you do this a couple of times, playing a couple of random games, you can get a decent idea whether the position is more promising for you than for the opponent. So you played maybe 10 games, 100 games, 1,000 games, and then you gave it a score, like a percentage, indicating a kind of success rate. And you do this for all of your leaf nodes, and then you do some minimaxing. This has a slight problem, because if you would have looked one step ahead, then you would have seen that this averaging is not always a great idea. Could be that you have one great move and all the other ones are bad. And then you start to either to overestimate or to underestimate this position. Well, you could simply say, let's search one ply deeper and everything is fine. Only one small problem for this. Such a Monte Carlo evaluation takes a lot of time. So you have to hope that these simulations are more or less reliable. And what are they? What happens if they are not? Now, this limits the look ahead of your search. And the whole thing that we learned over the decades was that if you can search a little bit deeper, then usually you also play better. The deeper you can search, the better your result is going to be. There is a strong correlation for that. And Monte Carlo evaluations maybe give you an assessment, which is better than nothing, but the look ahead is limited. That was a problem. Until 2006, 2007, when someone said, you know what, this is wrong. You're building a tree, and then you start using Monte Carlo evaluation. No, you should first use Monte Carlo evaluation and then build your tree. So what this guy did, Rémi Coulon, in 9x9 Go, was simply say, well, simply let's start sampling until the end. And every time I'm seeing a new position, I simply add it to the tree. And if I revisit the position again, then I keep track of the statistics, how successful I was. And at a certain moment, I'm building a tree like this. So what you do, all the time, you're going back to the root node, and you start selecting a path that is interesting. Here, I was very greedy. I went to the positions that looked very promising for me, and assuming that the opponent wants something different, he tries to reduce my winning score. And then you will get into a so-called leaf node. You start adding a node, and then you play a complete random game, you score it, and then you start to backpropagate it along the path that you have visited. So basically, you will adjust the averages and you will also adjust the counter. Simple as that. Now, he was very successful with this 9x9 Go, but he had one small problem. This is a little bit greedy, because you could have been unlucky in certain areas and you start simply to discard them. How are you going to balance this? And this is a problem that we also see in reinforcement learning between exploitation and exploration. On the other hand, on the one hand, you don't want to spend a lot of effort in bad lines, and you would immediately like to dive in the more promising ones, because that is going to be your plan of action. On the other hand, it could have been that some positions were seemingly looking bad, but if you would have investigated them a little bit better, they could have turned out to be Nice. That is so-called exploration. How are you going to balance this? Because you only have a limited amount of time. Let's go back to Monte Carlo. If you go to Monte Carlo, you have these roulette wheels maybe, but you also have slot machines. And a slot machine is also called a one-armed bandit. The reason why a slot machine is called a one-armed bandit, in the long run, you'll always lose your money. In the good old days, for those who have read Lucky Luke, basically you had to pull an arm, one arm, and then you hoped that you would also get some coins back. Now, in the multi-armed bandit problem, you go to a casino and they have different slot machines. Big slot machines, small slot machines, the slot machines where you get 1 million euros, the small slot machines where you don't have to put a lot of money in that. You would like to find the slot machine that gives you the best payoff without putting too much time in it or not putting too much quarter in these things. Now, around the 2000s, people started to investigate it, and there is an algorithm called UCB, Upper Confidence Bounds, that gives you a couple of guarantees that you will find the optimal slot machine in a certain amount of time. Now, one of my former roommates, office mates, Levente Kotschis, then said, okay, let's use this ID at every level of your search tree. And that's called UCT, Upper Confidence Bounds Applied to Trees. A very original name, very successful. So basically what you do, if you're in a state, you have several actions. You know how many times you have played an action, basically how many times you pulled the arm. You also know how successful you have been for a particular action. And then for all the actions, you will start using this formula in order to select the one you're going to investigate. Now, this is a balance between exploitation and exploration. So the first term, which I call value, indicates the score so far. And the second term is basically the exploration factor, taking into account basically how many times in that particular state you have pulled an arm, and I have to see if this is going to work. Yes, I call this NP, P of parent. The number of times you pulled that arm, and then you use the square root and an ln and a c. And this is all mathematically because it assumes a stationary distribution, which is not the case. Now, how does it work? Now, basically, it tells you, well, if I'm pulling or putting some quarters all the time in one particular arm, this NP is going to grow over time, which means at a certain moment, the ones that you didn't find interesting, well, will get a kind of bonus. Just like playing in a casino, you're always playing on your favorite slot machine because it's giving you a nice payoff, but sometimes you throw also a couple of quarters in the other one. And it might be the case that suddenly they turn out to be nice, and then of course that VI is going to rise. Now, it will guarantee that in a two-player game, in the long run, you will go to the right optimal line. Okay, that's nice. Now, over the last 10, 15 years, people started to enhance this whole Monte Carlo tree search framework because this is only the start. So what people actually discovered was that basically if you're using this UCB, it's also smart to start biasing it. And why is this the case? Now, the issue with the whole UCB is, you need to have some data in order to make nice decisions. However, if you're all the way down the tree, you haven't sampled that position that much. So basically, it's playing more or less randomly. So what people are doing is they start to bias that based on some knowledge. That can be by using some neural networks. It can also be the case that you simply look at how an action performed overall, how well it did, or how well it did in the neighborhood of that particular state you currently are investigating. And you basically are gathering all kinds of statistics. And then in the beginning, you use more of this general knowledge in order to make the right call. And over time, you start to learn for that particular state what is the best way to go. This is basically a two-speed online learning system. And there are many ways of doing that. The good part of these kind of techniques is they are pretty domain independent. So basically, when you're searching, you also learn what is a nice move or nice action overall. Now, in the simulations that you make in the end, if you are outside the tree, also people have been biasing that. Certain actions are usually a little bit smarter than other ones. For instance, in Go, if you can capture a large set of pieces, then always do it. The disadvantage is, again, you're throwing in some domain knowledge that you don't want. And here, what you again can do is take into account how well an action performed overall, or how well an action sequence performed overall. Basically, people are using the good old-fashioned idea of n-grams, saying, well, an action, how good it is also based what the opponent did and what you did beforehand. So basically, they look at the action sequence. And then more or less taking a kind of greedy selection way of selecting the moves during that play out. Now, epsilon greedy simply means in epsilon of the times, you do something random, and in greedy, you play according to policy. A classic idea from reinforcement learning again. And again, there are many people who have worked on this. Now, I lied a little bit. People are not playing until the bloody end. Yeah? At a certain moment, you can start assessing how well you are doing. For instance, if you play a game of chess, if you are 2 rooks ahead and a queen ahead, please call it a win. You're not going to play until the bloody end anymore. So this is so-called using a kind of cutoff, and you can make it very dynamically. And that can be based on some domain knowledge, can also be based on some learned knowledge. And the better the knowledge is, the smaller the simulation is going to be. So dependent on the amount of knowledge you have about a domain, you either have to simulate till the end, or basically when you start simulation, you can say, oh, you know, I have a pretty good guess. Monte Carlo can deal with both modes, no problem at all. And the last thing that we did was, okay, you have all these parameters. To do the epsilon greedy. Now, epsilon, is it a 5% of the time random? Is it 10% of the time random? You see this UCB, there are also kind of constants to balance exploitation and exploration. At the moment you set them, well, it can become suboptimal if you're playing against a different opponent, or in a scheduling problem, you get different use cases. So we also had a mechanism based on some evolutionary algorithm that during the search, we also could actually tune them and readjust them. Because we're collecting a lot of simulations and we can learn whether these parameters are actually smart or not so smart. So there are ways to actually tune them. We used an n-tuple banded evolutionary algorithm for that. It's quite nice, but I'm not going to explain this. Now, in the end, the boys of Google DeepMind use this whole MCTS mechanism to defeat the best human player. And they use also neural networks for that. So they had 2 types of networks, which they later integrated. And one was a so-called policy network, which could actually predict what would be a nice action, and use that to bias the UCT mechanism. That was so-called the PUCT, which I'm not going to explain. And the other one was a value network. Basically, they use that in the simulations in order at a certain moment to simply cut them and give basically an estimate what the outcome of that position would be. So policy is more like, okay, what is the nice, what is a nice, interesting action? Whereas value network simply assesses or makes an estimate of the position. And this is a nice combination of using machine learning and reasoning. So far, I think in the discussions during yesterday evening, people said, okay, we're doing all this machine learning stuff, but maybe we sometimes also should think a little bit what we are doing. First, what they did was they looked to human game records to train these policy networks and these value networks by using deep reinforcement learning. Later on, they said, well, okay, what will happen if we don't use human knowledge? And this is so-called the AlphaGo zero approach. Zero knowledge. Huh? Like in Coca-Cola, you have nowadays zero sugar. Human knowledge is sugar, huh? not very good for your system. Huh? It's too biased. So basically what they did, they used the standard MCS, let it play against itself, and use a neural network to learn what are nice actions and what is the estimate of the outcome of the game. Of course, that's not playing very well. But that neural network at a certain moment gets a clue what's good and what's bad. It's like, it has an idea like an amateur. Next step is you integrate these networks and let them just play again. Of course, now playing a little bit better. And then again, use neural networks to analyze these games and learn what are nice actions. So basically, the MCTS becomes a tutor of the neural network. So basically, an AI is tutoring another AI, and that becomes then a closed loop. Now, if you do a trick like this, by the way, they needed a lot of hardware. I think a $25 million machine for this. So don't try to do this at home. Even with the modern video cards, it's still quite a big job. That network was able to get on its own an ALA rating of 3,000 ALA points. Now, 3,000 ALA points is playing like a grandmaster. So it had a good intuition what a good move is and what a bad move is. But it was not taking a hand. Because if you then throw MCTS on top of this, it went to 5,000 ALA points. So an additional 2,000 ALA points. Now, the difference between 5,000 ALA points and 3,000 ALA points is like, forget about it. No chance in hell that you're going to beat me. And if you beat me, then I will give you $1 million. That is basically the difference here. And you can make a bet like this. Could also be a casino game. Yeah, okay. Never mind. Anyways, over the decades, people have been using MCTS in all kinds of games, ranging from puzzles to multiplayer games, which is with multiple players, which is always a headache because you have some players that can simply throw away the game, and you have to deal with that. To games with uncertainty, where there is chance, where you don't know where the opponent is, until even these arcade games, where in real time everybody is moving around and you still would like to make a plan. So you make continuously, you make a plan, and in the meantime everything starts to change. However, Monte Carlo can deal with this noise quite good. So here's one of my students, very proud, actually showing that his agent beat all these other Pac-Man boys. Now, anyways, in Maastricht, in the last decade, we had a couple of PhD theses dealing with this. Now, there's one thing, even that this MCTS is doing very well in many games, there is no free lunch. So most of the time, this is pretty well engineered for a particular domain. The nice part is it is a mechanism that works well in a score to many domains. So the question is, can we make it in such a way that it becomes more generalizable, like that we would like to achieve in so-called artificial general intelligence. Because in artificial general intelligence, we have to promise that we are going to build systems that are playing board games, can talk to you, analyze data, compose music, solve mathematical equations, and also drive a car. Now, these large language models can do a couple of them, but not all of them. So an AGI should be able to perceive, to act, to communicate, to learn, and also to plan and make decisions. And this is where I come in. Now, currently, in our game playing community, we are going back to square one. So what we nowadays are trying to build systems that can play any game at any time without using a lot of time to learn this game from scratch. Basically, it's like how I would teach you a game. I come with a game and you simply start playing it. And after a couple of moves, you will figure out what's good and what's bad. You learn the rules, you start thinking about it, and you start already playing reasonable. In 2005, in Stanford, they came with a general game playing competition, where basically you had to design an agent that would get then a couple of games. You had to play against another agent, and you didn't beforehand which game this was basically was. Now, Facebook have now also set up their own benchmark called so-called polar games. So all these big institutes are interested in this general game playing, because this is a nice benchmark for search algorithms, but also for machine learning. It's even crazier that because there's also the so-called general video game playing competition, where your agent has to play all kinds of games without knowing beforehand which games it's going to play. And you see everything is moving around like crazy here. Now, and again here, MCTS bots are usually the strongest here. We won once the competition. Now, the issue is that these search algorithms have to address a wide variety of games that are unknown, and MCTS is very successful because it can deal with the fact that it doesn't get any domain knowledge. It's so-called a heuristic. Still, the issue that we see here is that even these MCTS bots are very good, they always fail on 1 or 2 games. And there's no configuration which is always doing very well. And that is usually very annoying. So there are a couple of techniques. What people do is so-called online parameter tuning, or even using a whole portfolio of MCTS search algorithms that simply search in parallel and then simply make a vote in the end. So, which, according to them, was the best action. Now, this talk was about Adaptive-Monte Carlo search and its application to science. And so far, we only have been in games. So I haven't fulfilled my promise so far. So now, what I'm going to do now is to give you a couple of examples to use search in the real world. And I will show you how some of these game AI search techniques actually work. So nowadays, there are maybe hundreds of papers where they use MCTS for all kinds of scheduling, optimization problems, and even using them in drones to make plans. I will show you 3 of them where we were involved. The first use case was a company in Germany who built these huge prediction facilities to plate parts, like car parts or plane parts, to give them a nice layer, like a chrome layer. Now, this is always a very complex process. And the issue was there is that these production lines are big. You have 100 machines. And at the same time, there are different components being processed, which have to use different machines. Moreover, this scheduling task is also a black box task. So at the moment you make a plan, then there is another piece of software that checks whether your plan is actually safe. So your final plan is different than the plan you actually gave it. And here, the whole goal was to simply decrease the make span. To make it the whole production process as efficient as possible. So what did we use? Yeah, of course, MCTS, but then a variant that works very well for the single player that we tested in all kinds of puzzle games first. Samagama, very popular. Then we used a couple of techniques that we took from the general game playing, because we don't know what good actions are, so we learn online then. We use some techniques from the real time. We also parallelized this whole stuff. And then in the end, we also learned or tried to learn what the job scheduler usually would do. So we simply learned the rewards. So we learned basically, if I'm giving a plan, then I will get a final plan. And then basically I know what my make span is going to be. And I'm using neural network to simply learn this. Now that neural network is of course not perfect, but who cares? I need to make a nice plan. And then we simply integrated this in our MCTS. So on the big problems that they have, typically around 6,000 jobs, 16 types, using 110 machines. These machines are also in parallel. We were able to improve the make span in average with around 10% compared to the software they were using usually. By the way, this was done in less than a minute. also it had to embed it in the system itself. So we couldn't use a big cluster to run this for ages. No, it had to be being done really in on time. Of course, also these jobs will change every day. So they really needed something that was quick, would give them a great plan. Yes. Other one that we did with Philips. Philips is not nowadays not making these light bulbs anymore. They are more in healthcare. I'm also looking at the time. Still good? Yeah, we started also later. 5 minutes. Okay, then we'll be quick. Here, they had a huge data set of patients that had heart surgery, and then they looked which services they got, and what was the chance that they would go back to the hospital a year later. Of course, in the United States, if you're being re-hospitalized, it's very expensive. It's 2 times, 3 times more expensive than Europe. And they simply wanted to learn, okay, what is the risk, or to predict what is the risk of being re-hospitalized. And they built a model, and then they simply asked us, okay, can we then also, using that model, to come up with a better care plan that would reduce that risk for unknown patients, for new patients. Again, here we use MCTS, and we were using all kinds of techniques, actually coming again from general game playing, because we have no clue which game we are playing. So therefore, we use these techniques. And then on some preliminary results that we had, we saw that the plans that we were able to make compared to the plans that the clinician would make would in average have a 12 points risk reduction of re-hospitalization, assuming that our model is the ground truth, by the way. And what we also saw was that in the bigger or the higher risk categories, you could even reduce it with a 40% risk reduction. We also validated this with the literature, and the combinations that it made were also validated by the medical literature. Of course, the criticism here was, okay, this assumes that the insurance will cover all services that are in the plan, which is not always the case in the United States. And the second thing that we assumed that we didn't care of the quality of life. Because sometimes you make also the plan that at least for the last couple of months, you still have a nice life. Simply this didn't take it into account. Now, we also had a case with structural engineering. That was something we did with the University of Aachen to put basically the load-bearing elements at the right spot for big apartments. You can use genetic algorithms for that, but the MCTS turned out to be coming up with quicker solutions. So this was a nice thing that we did. I skip this now because I still want to use the last 3 minutes for something else. So MCTS works very well if you even have multiple cores. It parallelizes it very well. But the question is, can we get more? Because nowadays we're going to have quantum computing. And one of the things in quantum computing is to solve particular problems, you have to set your quantum circuit. And a quantum circuit consists out of all these AND OR gates, who also are parameterized. And you have a kind of subfield called quantum architecture search that you try to find a nice quantum circuit in order to solve a particular problem. And we're using MCTS to automate this. So the MCTS is trying to find where to put the gates, which gates at which place. So it adds gates, it removes gates, it changes gates, and then it tries to find in an automatic way these circuits. Now, what kind of problems you can solve in principle if you would have a quantum computer is we're testing this on the ground state energy estimation, systems of linear equations, puzzles like Sudoku, max-cut, and even particle track reconstruction. And that is something that you do at CERN. Now, I have to say one thing here. Of course, we're using simulators because we don't have a quantum computer. It's no guarantee that we will have a quantum speedup because we need an MCTS first to set the circuit, and then you can actually solve the problem. And that is not a quantum speedup because I still need the MCTS first to do it. And even that is not clear if there will be speedup at all. So Now, this was a quickie. Our MCTS approach is actually doing well because we are able to build a very small circuits, which is always nice because then you don't need a very big quantum computer. And we also do this in a quite fast time with the same solution quality using MCTS and all these game AI tricks. So that is fun. Okay, I still have 1 minute. Yeah, I will skip this one. Now, in the end, and that's the last thing I would like to discuss, what is now happening? If you didn't understand anything I told you so far, that's great. Because at the moment you're doing this MCTS, you will see that you are a little bit more successful in other places than in other directions. And usually it gives you back a percentage, like 62% success, 58% success. Therefore, I'm going for the 62. A difference of 4%. Yeah, very interesting. If you then start to analyze the why, you will go down the tree. These statistics will go all over the place because the more you go down the tree, the less you have sample, the less it becomes also unreliable. So this is also not a great explanation. And then if you're going to look in the simulations themselves, well, they were selected by an epsilon greedy n-gram type of techniques, which was cut off by a neural network as well. Very nice. And we came there by using some UCB, and then we parallelized the whole thing. So we were developing this tree in parallel. And by the way, we also were tuning at the same time online all the parameters. And maybe we use another AI to construct this whole thing. And in the end, we also ran it on a quantum computer. Since a couple of years, we started a kind of subdiscipline in AI. So we have explainable AI that usually tries to explain all kinds of machine learning and methods like neural networks. There's also explainable search that tries to explain why we went for a particular direction, and even more harder, why we didn't go into a particular direction. And that is something that we nowadays are looking at. As I have still like 30 seconds, I will go to the conclusions. I hope that I've convinced you that Monte Carlo search is a very powerful AI tool. You can combine it with all your nice machine learning techniques and you get something even better. Still, we have a couple of open questions. Can I also use it in your domain? How can we make it as generic as possible, that we don't have to do a lot of engineering? If we have these quantum computers, how to use MCTS then? And then in the end, can we also explain their decision making? Thank you for listening.
Thank you, Mark, for the great talk. Questions? Okay, maybe while they're warming up, I just wanted to understand a bit better. So I'm not from this field, but this general game playing.
Yeah.
So it works like that you train it, you optimize your MCTS for one game, and then you let it learn. I mean, so yes, this is going, I mean, how do you optimize the tree and on all the machinery, and then how you...
Yeah, so basically what happens in general game playing, your engine gets like 30 seconds in advance to understand the game.
So it plays it a little.
And then really it starts to play against an opponent who also doesn't know the game it's playing. Yeah. And then the whole trick is that during the playing, you already start to learn how to play the game. Okay. And the way you learn it is basically you also do the search. And during the search, you also will learn what are usually our good actions and bad actions, and you can use that information in order to make the search better.
Okay. So you do not pre-train it; you just make an.
Yeah, no pre-training. No, it has to do. It has to do with
every game is.
It has to do it on the spot.
Okay, now it's clear. Thank you. Yes.
I will ask you, in what way do you make Monte Carlo research self-adaptive? So how to choose these parameters like C and so on?
Yeah. So I was very quick here because we're using this NTBA here. And how we do it in the two-player is simply to take into account is that In the beginning, it can still play around with the parameters, and it can see in simulation if with that particular parameter for that player, it was able to defeat the other player who is also tuning parameters. So you make it a kind of competition here. But both agents in the search are adjusting their parameters, which means at a certain moment you will converge to a particular setting. That's the way how we do it. You can do it quite easy if it's adversarially. At the moment it becomes really single agent, it becomes a little bit harder because it could be that you start overtuning it. Yeah.
Okay.
Yeah.
Thank you.
Hi, thank you. I mean, in this talk, we have also seen AI, not necessarily with machine learning, because exploration, the search space. What I was wondering was, you optimize one single measure, right? It is not multi-objective optimization, right? Because as far as I understand, this is easily extendable, no, to multi-objective optimizations. So from the neural network that I see here, I see only one output. So I assume it is only
so
one.
The simplest one, that's always a very interesting single a multi. There is some research to do it actually for the multi-objective case. Sometimes we simply sheet, and then we have a multi-objective case, and then we put everything together and we weight it, and then we make it single objective again. So for instance, this one here was actually multi-objective because we tried to improve the make span and the lateness at the same time. Yeah. And the trick is, that is a trick. What people do, they simply combine the two and then they make it single again. There are also MCTS agents that are truly multi-objective. Yeah. Sure.
Since you are solving optimization problems, how does this compare, let's say, to evolutionary approaches for optimization?
Yeah, so there have been comparisons with that because you can, in many of these examples, you can also use a genetic algorithm or an evolutionary approach. What the nice part is of MCTS, it still remembers the overall view, because the danger with an evolutionary approach is at a certain moment you go into a particular direction. And at the moment you go into that direction, tracing it back can become a little bit complicated. So people have comparing MCTS, also a variant called nested Monte Carlo search, on these optimization problems, and you see that it outperforms quite a lot of them. Yeah, but for a single agent, there is a variant called nested Monte Carlo search, which is superior than MCTS.
Okay, thank you, Mark. Let's thank Mark again.